Hello, this podcast is on the conservation of mechanical energy. Specifically, we're going to be looking at what is mechanical energy. We're going to look at what potential energy is and how to calculate it. We're going to talk about conservative and non-conservative forces, very important concepts when we're dealing with mechanical energy. Then we're going to look specifically at the conservation of mechanical energy, see the role that conservative forces play in potential energy, and lastly, take a look at non-conservative forces and kinetic energy and the relationship between the two. And along the way, we're going to be doing some examples and solving some problems. So let's move on and talk about total mechanical energy. This is the energy stored in a particle's kinetic, gravitational potential, and elastic potential storage mechanisms. And our equation for that is simply E is equal to K plus U, and we can break U down even further into its gravitational and elastic potentials. So let's look at calculating mechanical energy. Off to the right here, we have a situation where we have a ball that is a height h above the ground, and it's in the gravitational field. We'll assume Earth's gravitational field, and so the ball is going to start with an initial velocity, and it's going to be an initial velocity of 0, and it's going to be dropped and falling. In our specific problem, we're asked to find the total mechanical energy at point B. When the mass of the ball is 5 kilograms, the velocity at point B is 10 meters per second, and the total or starting height was 10 meters, and at point B, the ball has fallen 5 meters. Here's our mechanical energy equation. Now we have to take the K and the U and break it into more specific formulas that we can use to calculate the actual amounts. So for kinetic, it's equal to 1/2 the mass of the object times the object's velocity squared. And the gravitational potential energy is the mass times the strength of the gravitational field times the distance above or below the reference point. And in this case, we made the ground the 0 reference point. Notice we do not have any elastic potential energy. Well, we go ahead and plug in our numbers, and we find that at point B, the ball has 495 joules of total mechanical energy. Let's move on and talk about potential energy. This is the energy stored in a particle's or object's position in space or physical configuration. And potential energy can perform work on particles and objects. Here's our equation relating the change in potential energy and the amount of work performed, and it tells us that the work performed is equal to negative the change in potential energy. And of course that flips the order of our initial and final potential energies in this subtraction. As we discussed earlier, there's two types of potential energies. Let's take a closer look at each one. First, we'll look at gravitational potential energy, and this is the energy stored in a particle's position in space. In other words, the particle, no matter where it is in the universe, is going to be in some gravitational field, and it has the potential to move towards that center of the gravitational field. And that means there's energy stored in that space or distance above the center of the gravitational field. And our equation for that is the potential energy is equal to the mass times the strength of the gravitational field times y or h. We sometimes use them interchangeably. Y and h are simply the distance above an arbitrary reference point. We typically set that reference point at the lowest point the object will get in its motion. And in this example, the box is going to be stopped by the floor. So we would set the floor as our 0 reference point, although that's completely arbitrary. In this case, when we're talking about gravitational potential energy, the work is being performed by gravity or the gravitational field. And our equation for that is that the work performed is equal to negative the change in the potential energy. And again, you can see that flips the order of our initial and final positions. So if you're like me, when I first saw this, I right away said, well, why is work equal to negative the change in potential energy? Let's look at that. First, we need to remember the flow of work. If work is positive, that means the energy is flowing into the object feeling the force. Or in this example, if work is positive, that means that energy is flowing from the gravitational field into the falling box. If work is negative, then energy is flowing into the object exerting the force. In this example, that means that energy would be flowing into the gravitational field, and of course that means that it would be flowing out of the falling block. So looking at this example, from Earth's gravitational field, perspective, as the block's position decreases and gets closer to the floor, the energy stored in the gravitational field, the potential energy, is decreasing. And from the block's perspective, as it's falling towards the floor, its speed's going to increase, so its kinetic energy is increasing, and that means its mechanical energy is increasing. Hence, work is positive because energy is flowing into the object feeling the force of gravity. Finally, if the gravitational field is part of the system, then the force is internal, the energy flow within the system is internal, work is internal, and that means there is no external work performed. Typically, when we solve these problems, we do make the gravitational field part of the system. That way we can have potential energy in the system. So please remember that gravitational potential energy belongs to the gravitational field. If the gravitational field is part of the system, then your system can have gravitational potential energy. If you do not make the gravitational field part of the system, then that potential energy lies outside the system and your system will not have any gravitational potential energy. Rather, that'll be recognized as energy transferring into or out of the system via the work transfer mechanism. Let's move on and look at the other potential energy, elastic potential energy. And that's the energy stored in a particle's configuration, more commonly known as being stored in its temporary stretch or compression. Most often we're looking at springs when we're talking about this, but it could also be rubber bands, bungee cords, rubber balls, things that have tennis balls, things that have the ability to temporarily compress or stretch and then return to their normal shape. This is our equation for calculating the elastic potential energy. It's 1/2 times K times X squared, where K is the spring constant, keeping in mind that stiffer springs will have higher spring constants, and X is the distance of stretch or compression beyond the normal shape. We often call this normal shape the equilibrium position. The work performed by the spring is equal to negative the change in the elastic potential energy. Again, we ask ourselves, why negative delta U sub S? Thinking back again to our workflows, positive work means that energy is flowing into the object feeling the force. In this case, energy would be flowing into the block. Negative work means that energy would be flowing into the object exerting the force. In this example, that means that energy would be flowing into the spring, and of course it would be coming out of the block. Let's look at this from the spring's perspective. When it's launched, its position, X, is decreasing because it's getting closer to the equilibrium position of 0, and that means that the potential energy stored in the spring's compression is also decreasing. Looking now from the object's perspective, it's going to start moving and speeding up, so its kinetic energy is increasing, which means its total mechanical energy also increases. Hence, work is positive because the energy is flowing into the block, which is feeling the force. Finally, if the spring's part of the system, then the force is internal, energy flows within the system. We say that work is internal, and that means there is no external work being done. So we typically will make the spring part of the system along with the block. However, if you make the spring part of the surroundings, then we have to keep in mind the block can have no potential elastic energy, because that goes with the spring. So if you want your system to have elastic potential energy when you're solving this problem, you need to make the spring part of it. If the spring's not part of the system, then the energy it imparts to the block will flow through an external force and be external work. Let's work through a simple problem on calculating potential energy. Here we've got a pop gun. It has a spring that's compressed from its equilibrium position, and it has the ability to launch this ball. So find the potential energy of the 50 kilogram bullet when the compression is 1/10 of a meter and the spring constant is 150 newtons per meter. Here's our potential energy equation. Notice we have both gravitational potential energy and elastic potential energy because we have a change in the position of the spring, but we also have a change in vertical position, also known as height. So we go ahead and plug in our numbers. This first part is calculating the gravitational potential energy. Notice the negative sign in here means that energy is flowing out of the ball when we compress it from this 0 point. And then here is our elastic potential energy. Notice regardless of whether the spring is compressed or stretched, the elastic potential energy is going to be positive because energy is being stored in the compression or the stretch. Whereas with gravitational potential, energy is lost. Energy flows out of that potential mechanism if the ball moves closer to the center of the gravitational field. We go ahead and plug in our numbers and we find that this ball has 0.7 joules of potential energy. Now we're going to move on from potential energy and talk about two important forces or types of forces, conservative and non-conservative forces. With a conservative force, the work performed by the force is independent of the object's path. The force performs no work on an object that starts and finishes in the same position. The two most common examples of conservative forces are gravitational fields and springs. Non-conservative forces are different. If an object starts and finishes at the same position, work is being performed and energy is being dissipated along the path. So that's different than conservative forces, where if an object starts and ends at the same spot, there is no change in energy and no work was performed. But regardless of the path taken, with non-conservative forces, energy is dissipated along the entire path so that even if an object winds up back at its starting point, work was done to get it there. Most common examples of non-conservative forces are friction and drag. So let's take a look here. We've got 4 different inclines. The balls all start at the same height and they'll all end at the same height. Without friction, in other words, with only the conservative force of gravity acting on it, the same amount of work is performed in all 4 instances as the ball rolls down to the bottom, and the ball will be at the same speed at the bottom of the ramp in all 4 cases. If we take the ball when it reaches the bottom of the ramp and we push it back up to the top, we'll find that the amount of work performed on the ball to move it back up to the top is equal in magnitude to the amount of work the gravitational field performed on the ball to move it to the bottom of the ramp. These workflows are in opposite directions, so when we return the ball back to its original position, the net work performed on the ball is 0. And that's what we mean by this definition up here. Force, the conservative force, performs no work on an object that starts and finishes in the same position. However, if we have friction, a non-conservative force, things are different. The amount of work performed in each of these cases is different. And if we measured the paths of each of these shapes, the incline that had the longest path would be performing the most, friction would be performing the most work on it. So I haven't measured these exactly, but my guess is that C has the longest path. Speeds at the bottom are going to be different, not the same. The path that is the longest is going to have friction causing the greatest impact, will be the slowest at the bottom of the ramp. I suspect that in these 4 cases, the ball at the bottom of ramp C is going to be the slowest speed. Finally, if we take the ball from the bottom of the ramp and have it go back up to the top of the ramp, we're going to find that there was work performed to have the ball go down and back up because we are dissipating energy because of the friction force, both going down and back up the path. Let's move on and talk about conservation of mechanical energy. Here's our equation. If energy is conserved, then the initial energy in the particle or object is going to be equal to the final energy in the particle or object. And of course, we can break that down into the components of the kinetic storage mechanism and the 2 potential storage mechanisms. So the system's mechanical energy is conserved when there are only internal conservative forces acting on an object. So this equation is true when only internal conservative forces are acting on an object. So an example of this would be something falling in a gravitational field. provided we make the gravitational field part of the system and we ignore air resistance or drag, which of course out beyond our atmosphere is a completely accurate assumption. Systems mechanical energy is not conserved when there are internal non-conservative forces or any external force acting on the system. So if you have friction or drag within the system, you are not going to conserve mechanical energy, and it doesn't matter what the force is. If it's an external force, even if it's a conservative external force, you're not going to conserve energy because those external forces are either going to be flowing energy into or out of the object they're exerting the force on. Let's talk about changes in mechanical energy. If you have an external conservative force, the change in mechanical energy is going to be equal to the work plus the change in kinetic energy plus the change in potential energy. When we have non-conservative forces, the change in energy equation looks similar, but there are some differences. First, we can see that instead of work, we have the net work. And also, I want to talk about, even though we have delta K and delta U here, they're not the same when we have non-conservative forces. And let's talk about that. If the non-conservative force is internal, some of the energy flowing between the kinetic and potential storage mechanisms is going to be dissipated and lost. If the non-conservative force is external, then some energy transferred between the system and its surroundings is dissipated instead of flowing into the kinetic. With non-conservative forces, our change in mechanical energy is not going to be the same. Let's solve some problems. First, we're going to look at the conservation of energy when we have a conservative force. Here's a problem. We have a single constant force acting on a 4 kilogram particle. It's asking us to calculate the work done by this force if the particle moves from the origin to a position specified by this vector. Does the result depend on the path? We need to explain that. Part B, what is the speed of the particle at position R if its speed at the origin was 4 meters per second? And finally, what is the change in its potential energy? We're going to assume that the system includes both the particle exerting the force and the particle receiving the force. That way we can count the potential energy as being within the system, and that makes answering problem C a little easier, a little more straightforward. First thing we need to notice in calculating part A is that the direction of the force is not parallel to the direction of the displacement vector. So we need to use our cosine theta formula. So work is equal to the magnitude of the force vector times the magnitude of the displacement vector times the cosine of theta, where theta is the angle measured from the displacement vector counterclockwise to the force vector. The beauty of unit vector notation is that we can break this work into the work done by the x component of the force against the x component of the displacement and the y component of the force and the y component of the displacement vector, and then we can just add them up to get the total work. So again, in the x-axis dimension, the work done is the x component of the force times the x component of the displacement times cosine 0, because both of these are in the same positive direction in the x dimension. Now when we get to the y dimension, the y component of the force is 5 newtons. The y component of the displacement is -3 meters. So we put the magnitude in as 3 meters, but because it's in the opposite direction of the force, we're going to have 180 degrees separation in the vectors. That gives us a theta of 180. And of course, when we do the math, we get a -15 joules. And when we add the two components up to get the total work performed, we see that it's -9 joules. That means that 9 joules of energy is flowing out of the particle that's moving. We were asked if this result depended on the path, and it does not, because this is a constant force, so it makes it a conservative force. It's not changing directions, like a friction force might change directions as the particle moves. So this is a conservative force. Now on to B. What's the speed of the particle at R? Well, our kinetic energy is going to be changed by the amount of work that this force performs. We need to find the final kinetic energy in order to find the final velocity. So we go ahead and take this equation and we find that the final kinetic energy is equal to the work plus the initial kinetic energy. We found the work done in part A. We know from the problem definition that the initial velocity was 4 meters per second, so we can use this equation to find the initial kinetic energy. We find out that the final kinetic energy is 23.0 joules. We can put that into our kinetic energy equation and we come up with a final velocity at position R of 3.39 meters per second. Finally, we're asked to find the change in potential energy. Well, because we made the force part of the system and because the force is conservative, we have an internal conservative force, and we know in that case energy is conserved. So the change in potential energy is just equal to negative the change in the kinetic energy. So we know that the potential energy gain of 9 joules. So the system gained 9 joules of potential energy. Now we're going to look at a problem involving non-conservative forces. Here we have a modified Atwood machine. We have a hanging mass that's going to drag this block along a table, and there is going to be friction involved, so we're dealing with a non-conservative force. So the coefficient of friction between the 3 kilogram mass and the surface is 0.4. The system starts from rest. What is the speed of the 5 kilogram mass when it has fallen 1.5 meters? So the friction is here between the block and the table, and we're asked to find the speed of the hanging mass. We want to treat the friction force as external and the gravity force as internal. The reason we want to do that is that it allows us to set up an equation where work is performed by friction, and that's going to be equal to the change in the system's kinetic energy and potential energy. Let's take a look at our setup here. This left-hand side is the equation for work. We know that the friction and displacement vectors are in the opposite direction, so it's going to be cosine of 180 degrees. This is the displacement, 1.5 meters, because we know that if this ball is falling 1.5 meters, this block is moving 1.5 meters to the right. The friction force is going to be the coefficient of friction times the normal force. Moving on to the right-hand side of the equation, this first term is our change in kinetic energy, and we have to include both masses because the system includes both masses. We have the final velocity minus the initial velocity squared, and of course the initial velocity will be 0. This last term is our change in potential energy. Notice I'm only dealing with mass 2 because mass 1 is moving horizontally, so there is no change in its potential energy. But there is a change in the potential energy of the hanging mass because it's moving closer to the center of the gravitational field. So we go ahead and rearrange this equation, solving for V sub f. That takes a little bit of algebra. We go ahead and plug in our numbers, and we wind up with a final velocity after the ball has fallen 1.5 meters of 3.74 meters per second. Now we're going to move on from conservation of energy and look at the relationship between conservative forces and potential energy. If we have a conservative force acting on a system that starts at rest and ends at rest, then we know that the work is equal to negative the change in potential energy, or U sub I minus U sub f. We can substitute this integral for work, and that leaves us with this expression. Starting from there, we can come up with a potential energy function. We go ahead and rearrange this equation for the final potential energy in the x dimension. That's equal to negative the work integral plus the initial potential energy. If the initial potential energy is 0, then our equation for the final potential energy in the x dimension is equal to negative the integral f of x, the force in the x direction, dx, evaluated from x sub I to x sub f. We can look at a conservative force function. For an infinitesimal displacement, we know that du is equal to negative f sub x dx, where du is the infinitesimal change in potential energy caused by a force acting parallel to an infinitesimal displacement. And we can rearrange that and come up with the force parallel to the displacement is equal to negative the derivative of the potential function with respect to the displacement x. Let's take a look at how we use this. And we're going to calculate force from a potential energy function. So we have a potential energy function for a two-dimensional force, and it is u equals 3x cubed y minus 7x. So we want to find the force that acts at the point xy. Because u is a function of both dimensions, that's why they call it a two-dimensional force. We have to look at each dimension separately. The force in the x dimension is going to be equal to negative du dx. So we go ahead and differentiate this expression with respect to x, and we come up with 7 minus 9x squared times y. And then we have to evaluate the y component of the force. So we're taking the derivative of the potential function with respect to y. And of course the force is equal to negative that. We're left with the y component force being negative 3x cubed. Therefore, we can write the two-dimensional force in our unit vector notation, 7 minus 9x squared y times I minus 3x cubed times j. Now, if we were given a specific value for x and y, we could plug those in, and that would give us our force in unit vector notation. Let's move on to non-conservative forces and kinetic energy. There are three ways to change kinetic energy. The first way is internal conservative forces, and in this instance, all energy flows from potential to kinetic or vice versa. Mechanical energy is conserved, so we know that the change in kinetic energy caused by internal conservative forces is equal to the energy transferred out of the potential mechanism. The second way to change kinetic energy is internal non-conservative forces. Here, energy flows from potential energy to kinetic energy and dissipated energy. So the difference here when the force is non-conservative is energy is flowing from potential, but not all of it's going into kinetic, like up here with conservative forces. Some of it is being dissipated. So the mechanical energy is reduced by this dissipated amount, and so the change in kinetic energy caused by internal non-conservative forces is equal to the energy flowing out of the potential mechanism minus the energy that's dissipated. The third and final way to change kinetic energy is with external forces. If the force and displacement are in the same direction, then energy flows into kinetic. If the force and the displacement are in opposite directions, then the energy flows out of the kinetic mechanism. The change in kinetic energy caused by external forces is equal to the work. That leaves us with an overall equation for the change in kinetic energy. It's equal to the change caused by internal conservative forces plus the change caused by internal non-conservative forces plus the change caused by any external force, either conservative or non-conservative. Armed with this overall equation, let's look and see how we can determine the amount of energy dissipated. I'm going to start with that overall equation we developed at the end of the last screen. We can restate this in different terms. So we know that the change in kinetic energy caused by both types of internal forces is equal to the energy that flows out of the potential mechanism minus the energy that's dissipated by the internal non-conservative force. The change in kinetic energy as a result of external forces is going to be equal to the work performed by conservative external forces less the work performed by external non-conservative forces. We can rearrange this and come up with the total energy dissipated is equal to the energy dissipated by the internal non-conservative forces plus the work performed by the external non-conservative forces. And that in turn is equal to the work performed by the external conservative forces minus the change in kinetic energy minus the change in potential energy. When non-conservative forces are external, in other words, we have no internal conservative forces, this relationship exists, that the net work creates the change in kinetic energy. All this is telling us is that the work performed by external conservative forces less the work caused by external non-conservative forces is going to create the change in kinetic energy. Let's take a look at calculating dissipated energy. A parachutist of mass 50 kilograms jumps out of an airplane at a height of 1,000 meters and lands on the ground with a speed of 5 meters per second. How much energy was lost to drag during this jump? I'm going to treat the gravity force as an internal force and the drag force as an external force. And the reason I'm doing that is that allows me to have no E dissipated internal, and it also allows me to deal with the gravity force through the potential energy equation. So I can take my base equation and rearrange it to the total dissipated energy is going to be the work performed by the drag force, and that's going to be equal to the negative change in kinetic energy minus the change in potential energy. So what we're saying is that the dissipated energy is going to be the energy flowing out of the kinetic mechanism plus the energy flowing out of the gravitational potential mechanism. Here's our specific equation to calculate that. And when we go ahead and plug in our numbers for mass, final and initial velocity, gravitational field strength, and height, we find that the energy dissipated by the drag force was 489,000 joules. So let's put this all together and look at a rather complex problem. We have a 10 kilogram block. It's initially 3 meters above the ground. It's going to slide down this surface, and this surface is frictionless except for this 6-meter patch between B and C. Then as it gains speed, comes down this surface, it's going to slow down a little bit because of friction, but it's going to hit this spring with velocity, and as it slows down and briefly comes to a rest, at the point it's briefly at a rest, this spring is compressed 0.3 of a meter, and lastly the spring constant is 2,250 newtons per meter. The question for us is, what is the coefficient of friction for the surface from point B to point C? First, we want to find the initial total mechanical energy at this position up here, position A. And we know from our total mechanical energy equation, it's kinetic plus potential. However, it's not moving and the spring's not compressed, so we only have gravitational potential. At the top of the ramp, the block's total mechanical energy is 394 joules. Second step, we need to find the final total mechanical energy of the block when it has compressed the spring and has come to a rest. This is our total mechanical energy equation. However, because the block is at a rest, there is no kinetic energy, and because it's at ground level, which is our zero reference point, it has no gravitational potential energy. It only has elastic potential energy. And so the elastic potential energy is 101.25 joules. Now, we know if we didn't have this non-conservative force of friction, we know that total mechanical energy would be conserved, but it's not conserved because energy is dissipated over this patch of the displacement. So we know that the change in total mechanical energy is the work performed by the friction, and we also call that the energy dissipated. We can go ahead and take our energy equation and rearrange it to find the coefficient of friction, because our change in energy is going to be equal to the work performed by the friction force. Well, that's going to be negative the friction force times the displacement. That is going to be negative the coefficient of friction times the normal force times the displacement. We just go ahead and rearrange that to find the coefficient of friction. We plug in our numbers and we find that the coefficient of friction is 0.328. This is a great problem to end with because it incorporates most of the concepts that we've learned in this podcast about mechanical energy and its conservation. This ends the podcast. I hope you found it helpful in understanding total mechanical energy, when it's conserved and when it isn't conserved. Have a good day.